Welcome to our webinar series Modernizing Your Geospatial Reference System, organized by the United Nations Global Geodetic Center of Excellence. Today we look into part 2 and introduce you to the static geodetic datum. But at first I would like to present myself. My name is Jan Dostal and I am seconded from German Federal Agency for Cartography and Geodesy to the UN-GGCE as technical advisor. In this graphic, you see the different elements of a geospatial reference system, and after the introduction to the topic in webinar part 1, today we will have a look at the static datum, here highlighted in the middle part of the graphic. The static datum is connected also to other parts of the geospatial reference system, like the time-dependent reference frame, which will be covered in webinar part 3, here on the left, and the height datum on the right, which will be covered in webinar part 4. We will answer especially question concerning what is a datum, why we actually need it, and to whom it serves. We will have a look at the realization of a static datum, talk about its application, but see also the limitation of static datum. At the end of this webinar, we will show you how to transfer from one static datum to another one with help of the 7-parameter Helmert transformation. But before we start talking about the static datum, we should clarify what we mean by the term datum. A datum is a point of reference. For example, the 0 point on a ruler is a point of reference for making measurements. And in geodesy, we create the geodetic datum for allowing measurements on, above, or below the Earth. Let's start by understanding why we need datums by using examples of how useful they are. For example, let us look at how we administrate our land. How do we find safe locations for new buildings, for example, above flood marks, or designed new roads? How do we legally define property boundaries? Where are the borders of our cities and countries? These are just some examples where a datum helps you. Everybody who needs to accurately define the position of features or align geospatial dataset needs a datum. For example, as shown for the datasets on the right-hand side, decisions such as where a new hospital should be built are dependent on information about all these datasets, including addresses, population distribution, topography, road networks, etc. This can only be done when all these geospatial data are referenced to the same datum. We use such data for purposes like land administration, cadastre, construction, land tenure, precise agriculture, and many other applications. Okay, so what is a static datum? A static datum means that the coordinates of features like roads, buildings, and property boundaries are fixed at a specific point in time, such as 1st January 2024, and do not change despite the ongoing changes in Earth's surface, like for example due to plate tectonic motion. As indicated with the red crosses in the graphic on the top right, a static datum is created and accessed using stable survey marks distributed over land. For each such survey mark, the coordinates are observed. On the bottom right picture, you see then an example of geodetic survey mark equipped with a permanent geodetic antenna that allows continuous measurement of this survey mark. Typically, it is advised to observe GNSS on these type of survey marks for more than 2 years for their stability. After this amount of time, it is possible to analyze the GNSS data and compute accurate coordinates which can be used as reference point in the development of a country's static datum. Continuous monitoring and analysis of the GNSS is then needed to monitor the stability of the survey mark. Using this method, a country's static datum is also aligned with such like the International Terrestrial Reference Frame, which is the reference frame that GNSS work in. To better understand a static datum, here we describe the differences between a static datum and a time-dependent reference frame. We will describe time-dependent reference frame in more detail in webinar part 3, but it helps to understand static datums by providing some distinguishing features now. With a static datum, the coordinates of features like roads, building, and property boundaries are fixed at a specific point in time and do not change over the time. This is useful for nation purposes because it is simpler to implement, simpler for people to understand, and simple for people to align geospatial data to make informed decisions. It is, however, not reality. In reality, the Earth surveys experience ongoing changes, for example, plate tectonic motion, subsidence, surface heave, glacial isostatic adjustment, etc. The time-dependent reference frame accounts for some or all of these Earth dynamics. For example, as we discussed in the last webinar, the Australian tectonic plate moves at 7 cm per year to the northeast. This means over the course of 5 years, the difference in the definition of a property boundary in a static datum and time-dependent reference frame like the ITRF 2020 will be approximately 35 centimeters. ITRF is the reference frame in which GNSS products, including position and navigation services we benefit from every day, are provided to users. For this reason, nation datums should be aligned to ITRF, either 2020 as the most recent realization or another. Let's have a short look at the International Terrestrial Reference Frame, the ITRF, as the most accurate global reference frame we have. On the picture, you see the globally distributed observation network of the ITRF. The different signatures mark different geodetic techniques that contribute directly to the ITRF, where the red dots mark the GNSS sites, yellow stars the VLBI radio telescopes, green diamond SLR, and blue circle the Doris beacons. You can recognize that on some observation sites, several of these techniques are placed together. This is necessary to link the different techniques together. As example, in Germany, the nation datum is a static datum and is aligned to the International Terrestrial Reference Frame. This alignment is realized by using German reference stations which are included in ITRF for the definition of the German static datum. In some regions, like Europe, Asia Pacific, and Americas, there exist also regional reference frames, which is kind of a denser version of ITRF in those particular regions with extra GNSS station included. The regional datum is therefore aligned to the ITRF and to the national static datum. These different reference frames cover different needs, but are related to each other. This is done by some points of the national static datum that are included by the realization of the regional or global reference frames. Now that we introduce the static datum, we can look how it can be realized. In general, there are two different ways how a datum can be realized. Remember, the purpose is to define points of reference in the country. First, in the box on the left, the geocentric one using GNSS, mostly with active antennas on chosen ground marks, pillars, and rooftops. Taking the observation from GNSS, they are connected directly to ITRF and therefore geocentric. The other one on the right represents the traditional way, mostly older, but in some countries still in use. This static datum is built via triangulation networks with passive ground marks and markers on elevated towers. These are not likely connected to ITRF. On the picture, you see an example of a triangulation tower. You can consider its height by relating it to the tree standing next to it. To realize the static datum, stable markers distributed in the landscape are needed. This can be ground marks, like on the right top picture, classical monumentation, like on the left top picture, pillars on ground with GNSS antenna or GNSS antennas placed on rooftops, or just a small marker on the ground like on the bottom right picture. As one GNSS station often serves multiple purposes, global, regional, or national, such a marker can have different coordinates in dependency on the datum. This allows to relate the different datums between each other. We had already a look at the different kinds of survey marks. Once the survey marks are built or chosen, the next step is to determine the coordinates of the markers and the relation between them. This is done by firstly making measurements and then analyze them in what is known as an adjustment of the measurements. This is often done as a least square adjustment. Finally, marker once implemented into the datum have to be continuously monitored for its stability. Now we show two different ways how the measurements are carried out. The first, as shown on the left, is using GNSS to make geocentric observations. The second, as shown on the right, is using triangulation, a point-to-point terrestrial measurement propagation from one marker to another. On the graphic in the left-hand side, using GNSS observation to the satellites allow indirectly to create so-called baselines, shown in red. That means the distance and azimuth information between survey marks can be calculated. On the right-hand side, the same information is measured directly using terrestrial techniques like a total station, electronic distance and azimuth measurement device. The next step is to adjust the measurement and define the datum. First, the data collection through observations on the markers is needed. The relation of the markers are achieved through a free adjustment calculation of observations without any constraint to already existing reference frame. In this way, we obtain an unconstrained network. In the second step, we relate this unconstrained network at selected points to already existing networks like ITRF. With this step, we align the local network to high-order regional or global networks. With this, we can define a static datum aligned with higher-order datums. We explained how to create a static datum that should not change coordinates over time. But we should ask ourselves how stable over the time this datum really is. Although the markers are firmly connected to the ground, they can still experience a movement in position. As the Earth is not a rigid body, but experiences dynamic changes, it influences also our markers and with that our static datum. For these dynamics, there are different reasons, like for example, tectonic plates movement, seismic and post-seismic deformations, post-glacial rebound, subsidence and landslides, anthropogenic influences like mining, or systematic changes given, for example, through tides or seasonal variations. To identify any changes at our static datum, we need to monitor the markers. This is usually done in different ways, either on daily and weekly basis by active markers, or through remeasuring passive ground markers in campaign. From the observations of the continuously operating reference station, so-called cores, we can create a time series. An example of time series for one GNSS site you can see on the picture on the right, where there are displayed the three components of the position, the east, north, and up component. The blue dots in the graphs represent the continuous observations for the individual components over the time. You can see the values vary slightly. The green dashed line marks then an earthquake event that caused a visible displacement of the station. The passive markers, on the other hand, has to be remeasured in campaigns. As a result of the monitoring, we can identify and, if necessary, remove outliers, identify trends or systematic variations. Based on the results, we can also create models for systematic changes and variations, as well as consider the residual errors that cannot be assigned to any systematic. The residuals from monitoring and adjustment of the static datum give us an information about the network quality. Here we show some basic scenarios how to adapt the static datum in dependency on its quality check result. In first case shown on the graphic, the monitored residuals are in tolerable limit. That is an indicator for a stable network. The second case shows that one particular marker moved. In the figure in blue color, this is identified as an outlier and this marker has to be removed from the network. In the next scenario, in green color in the figure, we include a new marker to the network. But before including, we have to observe the new marker over some time, so-called quarantine time. The next scenario shows a network densification. In this case, we don't just add one individual site. Imagine we introduce new static datum and would like include to this datum a set of already existing or new sites to densify and homogenize the network. We relate these new sites, in green in the picture, to the already existing network. Up to now, we showed just the changes adapting the existing static datum. But what happens if we find out that the quality of the datum doesn't meet our requirements anymore, either by degrading of the existing datum or through increasing of the requirements through technological evolution? This picture indicates such a distortion of the whole network. In this case, we would need a new static datum. Introducing new datum, we have to ensure a continuous alignment with the previous datum. Bref, by introducing a new static datum, it is necessary to transfer position between the static datums in different epochs. This can be done using the 7-parameter Helmert transformation between the two datums, which we will focus on now. Doesn't satisfy the old datum the given requirements, new datum is created at first independently, the same way we already explained before. For this purpose, we have the use also sign included in the old datum. Now we must link the two datums together with the help of transformation. The transformation between two datums is carried out by the so-called Helmert transformation. The points new x, y, z coordinates in the vector b on the left-hand side of the equation result from the original coordinates of vector a on the right-hand side of the equation plus the transformation parameters that are given through an rotation matrix containing 3 parameters related to each axis, translation vector with another 3 parameters, each of every of the 3 coordinate components, and a coefficient μ for taking in account the different scale of the two different datums. The graphic on the right displays the two different coordinate system in black and blue, in which the point P in red is described. The rotation parameters of the 3 axes are marked in green. The point shift, the delta xyz, is displayed as well as the scale, the stretch factor. Before starting using the Helmert transformation equation for a particular transformation between two given datums, the 7 transformation parameters have to be estimated. For this, we need common points that have known coordinates in both datums as well as an inversion of the Helmert transformation equation to solve the problem. The graphic on the right represents with the red crosses a survey marker in one static datum. Now, we include in the graphic with the blue dots survey markers in the new static datum. And now, marked in green, you see that some points have a coordinates in both static datums, points with red cross and blue dots. These common points can be used for the estimation of the 7 parameters. Once the transformation parameters between two static datums are known, any location can be described in both datums. Here we describe how it works in practice. Usually we start with point description in latitude, longitude, and height in the original datum. First, we convert these coordinates in Cartesian system representation, means in x, y, z vector. Then we transform the coordinates into the other datum, and at the end we convert the coordinates again in the latitude, longitude, and height representation of the new datum. On the right, you see now also a numerical example for core station in Alice Spring by transformation from Australian static datum GDA 94 in the new Australian static datum GDA 2020. The numerical difference in the coordinates is shown in red. For the described coordinate transformation, different online tools exist. These transformation services are free of charge to use. Usually, a file of coordinates list can be uploaded and converted. On the left side, you see the Australian tool for the transformation from the geocentric datum of Australia 1994 into the geocentric datum of Australia 2020. On the right side, an European tool to transform between different epochs of the European terrestrial reference frame is presented. At the end of the presentation, we summarize the key messages from today. Static datum helps to administrate land with coordinates which do not change over time. Static datum is realized via passive and active markers on the ground that are connected to the unified network. Static datum must be monitored for stability over time and, if necessary, adapted. And 7-parameter transformation allows transformation between different static datums at given epochs. So connect with us, that we are more than happy to answer further questions and to help you. See you in the webinar part 3. Thank you.